Assalamu alaikum, dear student. This is Wajid Shah, and I welcome you back to the video lecture session. Dear student, before going into the details of this topic, let me tell you that basically we have two types of the circuits, in which the first one is simple circuit, another is complex circuit. Simple circuit is that circuit which is having a single source of energy, a single source of consumption of the energy, or we can say that a single sink of the energy. And Ohm's law is applicable there. Because that's a simple circuit, simply we can write V is equal to I into R, where we have discussed that V is potential difference and IR is the potential drop of the circuit. But sometimes we encounter the circuits where there are more than one. Say for example 2, 3, 4, 5, 6 sources of the energy and more than one sinks of energies. So that becomes a complex circuit. So for that complex circuits we can use Kirchoff's laws. The main idea and main theme of the Kirchoff's laws and the Ohm's law is same. It's another manifestation for the law of conservation of energy for a simple circuit. It's another manifestation of the law of conservation of energy for complex circuits. So Ohm's law cannot be applied to solve the complex circuits. Let us, for example, we have a diagram also given in the book. Let me draw the same diagram like this. And this one. Now, dear students, this is a complex circuit which is having two EMFs, E1, E2, two sources of the energy and three sinks of the energies. This is R1, this is R2 and this is R3. So Ohm's law cannot be applied simply to solve this type of the circuit. So for that reason, we can use Kirchoff's laws. So, in this circuit, we can see that this circuit cannot be solved by simply series and parallel combination of the resistors and the batteries. So, there is a specific technique, specific concept generated by Kirchoff's to solve this type of the circuit. So, this was the introduction of Kirchoff's circuit. In order to solve such complex circuits, the German physicist Gustav Robert Kirchoff in 1824 till 1887, this is actually the date of birth and the date of death. Kirchoff's laws basically consist of two laws. One is called KCL, another is KVL. Kirchoff's current laws, Kirchoff's voltage laws. Kirchoff laws can be divided into two simple rules, KCL and KVL. Now, we will be explaining KCL and KVL individually, one by one. So, what is KCL? Kirchoff's current law. What is the statement of this law? The statement of this law is such that the algebraic sum of the current meeting at a junction in an electric circuit is 0. To explain this concept, let us have a diagram like this is a junction, and the lines which I am drawing now are actually the conductors, the wires. For example, this is point O, current I1, this is I4, this is I3, and this is I2. This is a junction. This is a point where two or more than two circuits or conductors can meet with each other. So from the diagram we can see that the direction of the two currents I4 and I1, they are actually directed towards the junction. They are entering into the junction, they are coming towards the junction. And the direction of the two currents I2 and I3 are away from the junction. This is to one side of the junction, this is again on the other side away from the junction. So by the use of the Kirchoff's current law, we can simply write that sum of all the currents meeting at a single junction in an electric circuit is 0. Or we can write according to this diagram, we can simply write that I1 plus I4 plus minus I2 plus minus I3 is equal to 0. According to this rule, applying to that circuit, we can write the equation like this. I1 and I4 are entering into a junction, so we can take them positive conventionally, and I2 and I3 are directed away from the junction, they are coming out of the junction, so we can take them as negative conventionally. So solving I1 plus I4 minus I2 minus I3 equal to 0. Again, I1 plus I4 minus I2 plus I3 equal to 0. Or finally we can write that I1 plus I4 is equal to I2 plus I3. This becomes again another statement of the Kirchoff's current laws, that sum of all the currents entering into the junction is equal to sum of all the currents leaving the same junction. This is Kirchoff's current law. Now again, we are going to explain Kirchoff's voltage law or KVL. Kirchoff's voltage law is basically another form of the law of conservation of energy. So, KVL. This law refers to the EMF and voltage drops in a closed circuit or a closed loop, and may be stated as, for example, this is KVL, Kirchoff's voltage law. In any closed electrical circuit, in any closed electrical circuit, the algebraic sum of all the electromotive forces or EMF sources and the voltage drops in resistors is equal to 0. Algebraic sum of all the EMFs and the potential drops of the circuit is equal to 0. Again, this is law of conservation of energy. For example, consider the diagram like this. This is a circuit diagram which is having EMF 1, EMF 2, resistor R1, resistor R2, and for example, we consider that the value of this EMF is greater than this one, so we can take the direction of the current along this circuit as anti-clockwise, current I. So from this diagram, we can prove, we can explain KVL. Like, the validity of the Kirchoff's voltage law can be easily established by referring to the closed loop A, B, C, D, A. This is actually A, B, C, D, A. This is a closed loop circuit in which some current must be flowing. Very importantly, let me tell you that we can think of the direction of the current by our own selves. We can take the current clockwise or anti-clockwise. But apparently, all of you must see that the current should always flow from high potential to low potential. So that's why I have assumed that the potential of this EMF E1 is greater than E2. So the current must be flowing from high to low potential like this, and the current will be flowing. There are a few assumptions, a few points which must be kept in mind, and the points is that if we are following the flow of the current across the whole circuit, so we must keep in mind the points. First point, a rise in the potential is taken positive. Rise in the potential is taken positive. What is meant by rise in the potential? For example, when the current is flowing through E1, inside the battery E1, the current is actually flowing from negative to positive terminal of the battery. So actually the potential is increasing with time. So we can take this increase in the time as positive. Again, second point, a decrease in the potential is taken negative. Decrease in the potential is taken negative. What is meant by decrease in the potential? Following the same route, following the same path, we can see that the current is going from high to low potential. So from high to low potential, we can see that the energy is decreasing, the potential is decreasing, so we can take this EMF as negative, this as positive. For batteries, the positive end is always at higher potential. This is a previous information. Every candidate, every student must have in mind that positive is always taken at high, negative is taken always at low potential. current flows from high potential to the low potential. This is another very important point that we should. I have already told you that the current direction is anti-clockwise. Depending upon the magnitude of E1, I have assumed that the magnitude is E1 is high, then E2. So the current should be flowing from this high to this low. Again, assume that the direction of the current either clockwise or counterclockwise. This is a relaxation for the problem solution. You can take the direction of the current are clockwise or anti-clockwise. So, third important point is that direction of the current is your choice. You can take it clockwise or anti-clockwise. So, having all these points in mind, I can write this equation like here. E1 positive minus IR1. Why I have taken this minus with IR? This is a resistance and the current is flowing through this resistance, so this is actually a potential drop. Potential drop basically decreases the potential energy, the electrical energy decreases, so that's why you can always take IR as negative. So this is minus IR. Again, this is E2. Now as we can see that the current is flowing from high to low potential, so we can take E2 as negative because of the decrease according to this point. Again, minus IR2 equal to 0. According to the statement, in any closed electrical circuit, algebraic sum of all the EMF sources and the potential drops of a circuit is equal to 0. So this is the statement, mathematical statement of this diagram. We can simplify like E1 minus E2 minus IR1 plus IR2 equal to 0. Or E1 minus E2 is equal to IR1 plus R2. So now this is very much clear. This is very easy to understand that this is the net potential difference of the circuit. This is current. This is the total resistance of the circuit. So it is very much similar to V is equal to I into R, which is Ohm's law for simple circuits. But here we can have Kirchoff's voltage law for complex circuits. Thank you and have a nice day.